I think so. Okay.
Okay.
Alex, dar practic cercurile alea care au roșii la tine sunt, ar putea fi asemănate cu niște tranzistori
Care?
care în momentul în care ai suficient semnal se activează, nu?
Care? Nu, erau numai ca să diferențiez. They were only here. I just colored them, so I just picked that image because it illustrates the difference between the neurons in the input layer, the ones in the hidden layer, and the neurons in the output layer.
My question is if they behave like transistors in the sense that when there's enough input, a transistor, when you have enough input,
maybe, I don't know.
It allows current to pass through it.
Probably, yeah. No, okay, cool. First thing first, very important thing to have in mind when training neural networks is always to have distinction between your training set, validation, and validation set. So usually you do your training and validate the efficiency of your training by using a validation set that was not used in training. So what you do is like start with like a set of, I don't know, 80% of images, train them, and after that test on the other 20%, and that's it. I'm going to prove, so first thing first, I'm going to demo the part with Minist. So you have this sample on GitHub, you can play with it. It uses Theano. Okay, it will start working. And after that I'm going to run the same code in the cloud, and you're going to see a difference between running on my machine and running on a GPU machine. Another cool thing that I wanted to show you when using Theano is, you see, that's my error function. Here I'm saying, I'm summing over all neurons, over all the square root difference over all neurons that I have in my neural network. And it's getting pretty easy, for example, to obtain the gradient just by calling this function, and Theano provides you with automatic symbolic differentiation, and that allows you to implement like this type of tensor calculus operations pretty fast and pretty easy. So basically the whole gradient descent is this part. Here I'm computing the gradient, and here I'm applying it. And that's it. You see, but instead of writing like, I don't know, for example, this is how, that's the code that I wrote, for example, when I was computing the gradient descent all by myself, you know. It doesn't look nice, you know, I have like lots of code, and yeah, it's not nice.
What do they use with no
I'm gonna get that. Okay, what I'm showing there, I'm showing the error, the total error, I'm also showing the precision. So in my validation set, there I say, okay, I'm having a close to 10% precision, actually 9.47% precision. That means that out of 100 images, I'm recognizing like nine of them. So that's it. But if I'm letting it run, usually I'm going to get better precision, and yeah, I can save this model to use it in a real application. Okay, so that's standard backpropagation for a feed-forward network. Now I'm going to demo a convolutional neural network. That's an adapted example. So here I'm defining an input layer, a convolution layer, a max pooling layer. A convolution layer, a max pooling layer, the hidden layer, and the output layer. So I'm going to run this code. It will take some time. Okay.
Do you have some actual images that you're using?
Yeah. So these are the standard Minist images. So
can you maybe show some?
Sure. So look, here's the result from the matplotlib. So these are the convolution kernels that I learned. And these are the actual images that were being used for test, and here's what the results. So I use like only a small percent of images, and that's why I obtained this type of very good results. So I trained over like only 100 examples and so. You can see it here in the code. These are the convolution kernels that I'm applying over my training set in order to obtain the features. So this can be seen as matrices of, I don't know, float numbers.
How do you define the feature?
For example, if, like in here, you see, if I'm going with this kernel, when I say that I have a feature here, because here I'm having an activation. If I would have to translate, like for example, to interpret the image in this area, I would say, okay, here I'm having like only, so I'm having no, I'm having a constant, I'm having no, how to phrase it?
Take a break and start.
No, okay. Okay. The kernels are not the features. They help me extract the features. That means that by applying this convolution operation, I'm obtaining numbers which are very representative for my image. For example, in this corner, I will have like only a series of 25, 255, 255, 255, 255, 255. On this area, however, I'm going to have like, I don't know, a series of 255s and some numbers that show me that I'm having some really valuable information there. But keep in mind that here, I'm also missing information from here. You know, like from this part. I'm missing nuances, I'm missing shades of gray, I'm missing, I don't know, other type of forms. But this filter allows me to detect the edges. But when I'm saying features, I'm saying numerical representation of, I'm saying, yeah, numerical, I'm saying numbers that are very representative for my image. So this part with the convolution is more related to the image processing area. The fact that you organize the image processing as a neural network, that's secondary. I'm not very sure if I was. Probably I wasn't, but
Go.
We can take it offline after that. So. Okay.
And
And after that, I'm going to show you how this works on a GPU machine in the cluster. So I'm going to run it again on my machine, the part with the convolution.
Does this show that your network made no progress?
Yeah, exactly. But let me think why. Sure. Only 1 second. So I'm going to run this example again, and after that I'm going to get back to the other neural network that I have that didn't progress, and I'm going to explain why. Because I just want to show you like how fast the whole thing goes when running in the cloud. So somehow this works like pretty fast somehow. Okay. But let me switch to this is what happens when you are running on a GPU machine. Okay. The same algorithm, the same code, without the visualization part. Okay, so let's get back here.
So, Alex,
Yeah.
what's your recommendation for somebody that wants to get started with the machine learning in general? Let's say like this.
So the thing is that I provided some links in here on GitHub. It's so you can start. So first thing first, you need Anaconda, which is like a Python distribution that contains everything from Matplotlib, SciPy, NumPy, Theano. Yeah, it has everything. You have like lots of tutorials here in deeplearning.net. Theano is the Python library that I use for for running the code on the GPU. But there's so here is a very interesting thing. So I think if you can see here, I obtained the error was yeah, so usually when you start training, because I play with some parameters. Only 1 second to find it. So each time when you start, for example, training a neural network, you have like what is called like hyperparameters, which are usually set like, I don't know, starting from a history of experimentation. For example, the size of the training batch, the learning constant, the momentum factor being used for, I don't know, for momentum learning and so on. All these matter, and for that reason, I don't know, there might be situations when you don't get them right. For example, have a huge training batch, and after that you have like also like a huge learning rate, and after that your gradient goes like that in all directions, so you will never get the learning. And I think I played with it right before the presentation because I had like several. Okay, okay, yeah, I modified it. So before that I had like a bigger learning factor. It was 0.5 or 0.2. I just modified it to like a smaller value, and now the whole training works again. So
you increase the batch size?
Sorry?
You increase?
Yeah, and I also increase the batch size. Yeah, to strengthen the
batch size means the training.
Well, yeah,
the part you use for training.
That's another interesting question. So the thing goes like that. Each time you want to minimize a function, you can do it like very. You have to be very mathematically correct. On the other hand, here you cannot afford, for example, to compute the error function for all the data in your training set. Imagine that you have like 50K images. That means you're going to have to compute, if you have to be to follow like the pristine ways of mathematics, you're going to have to compute the whole error function. That implying summing over all the output activations for each image in your training set, and that. But you don't have so much computing power. And after that, but on the other hand, you can say, okay, I'm going to go with the gradient descent for a set of, for one image. I'm going to go with the gradient descent. I'm computing the error for the next image, and so and so. So it's a stochastic method, but usually it works. So, but we can also discuss that offline because there are like several implications for that.
So I'm coming back to my question, which is to you and also to Marius. So both of you presented machine learning. So if somebody wants to get started, it's not coming from the science part. It's coming either from an expertise in a domain and also from hacking, from programming experience part. What do you need in order to get started with doing some predictions, playing with some prediction models?
So to understand the first derivative and the second derivative from Wikipedia, you need to know some Python, and it's enough. After that, it's only a problem of, I don't know, convex optimization or error minimization really. So it's nothing that complicated.
Marius, what do you think?
Yes, if you want to start with neural network, yes, you need that derivative. But if you want to start with other algorithms, you don't need them. If you want to go with decision trees or random forest or other kind of or genetic programming, you don't need that at all.
Yeah, that's true. So you also have to understand like I don't know, statistics, probabilistics, thermodynamics, because all the researchers in neural networks are coming from the physics domain. But the thing is that you're going to have to understand entropy. The second, yeah, I'm just kidding. So usually having a good mathematical basis and some skills, it's enough. And usually if you know how to minimize a function, it's okay. When you are talking about decision trees and probabilities, you are talking about like, you automatically imply that you have to know, like for example, entropy. What I don't know, entropy. How does entropy and probabilities relate to each other?
You mentioned just a moment. You mentioned gradient descent. You mentioned decision trees. Which are the most, when you're training based on the data, which are the most encountered, I don't know, methods that you see out there?
Decision trees cannot be.
No, they're totally different. I'm just asking, what are the things that you've seen mostly used?
For big data, I think we will go with deep learning.
With deep
because the training time for decision trees is larger.
Okay.
And also the memory use is bigger.
Okay.
And I think for really big data, deep learning is the way to go.
So we have one question. Alex.
Tell us a bit about how to combine, or how you're combining.
One question, yes.
Could be combined different algorithms with neural nets, things like genetic algorithms, right, to enhance the way neural nets.
Yeah. So for example, you have like you can have like a committee of neural networks that will work together in order to provide you with the best results. And after that, you're going to just do some sort of a voting. And I think that was a competition on Kaggle. It was auto group prediction challenge. You also have the code for there, but I couldn't provide also the input data and the output data. You're going to have to download yourself. The thing is, so the winning solution consisted of like 2 or 3 deep network implementations and some gradient boosting methods that imply like having like multiple random forests, multiple decision trees, and also their decision average somehow empirically from what I've read the paper, yeah, through voting. So usually what you want to do is like having like I don't know, a neural network committee, like many neural networks that will vote, and you're going to get, yeah.
Okay. I don't know, decide how you want to get that questions or
the person that will ask me
yeah?
about the restricted Boltzmann machine, or to imply the restricted Boltzmann machine is. Yeah, okay. Well, because I found that question interesting, so yeah. Thank you.
All right. We are a bit late, so the question is, are we taking a 10-minute break and then we are speeding a little bit over?